Assalamu alaikum everyone. Welcome to the course of real-time embedded system, and today we will continue our chapter number 9, that is of control system, and we will wind it up today. So let's get started with the software coding of PID controller. So in this slide we will talk about the software coding. A PID controller can be implemented quite easily in software. Consider writing a program in C to implement PID controller. It might consist of main function with the following loops. We create the main function to loop forever. So the main function that is you can see in this slide will loop forever. During each iteration, we first read the plant output sensor, read the current desired reference input value, and pass this information to function that is PID update. PID update determines the value of the plant actuator, which we then use to set the actuator. For setting the actuator value, we require digital to analog converter because our value will be digital and we have to convert it to analog. Note that reading the sensor will typically involve analog to digital converter and setting the actuator will involve digital to analog converter. Now, we are not going to include the details of these, how it works, digital to analog converter and analog to digital converter. So in this slide you can see that we have a main function and we have defined these variables: sensor value, actuator value, error current. Then we have PID data variable of the form PID data. So PID data is a structure and this function is initialize the actual values. PID initialize, so we initialize the values of PID structure. So this loops forever. We are reading the value sensor get value in this sensor underscore value variable. A reference get value, we are getting the reference value, and actuator value is basically once we pass on these values, reference, sensor and PID values to PID update, so we get the actuator value, and then finally at the end we set this actuator value. So let's move on to next slide and see how our PID structure looks like and PID update function works. So the PID underscore data holds three gain controllers, that is P gain, D gain, I gains, which we assume are set in the PI initialize, and we set these values in PI initialize. It also holds previous sensor value, which we will be used for derivative term, and it also holds cumulative sum of error, which we use for integral term. So as you can see here in this structure, we have P gain, D gain, I gain, and we also have the value of sensor value previous, which we use for derivative, and we have accumulative error, so which we are going to use for integration. As I have told you, for integration we require previous terms of error sum, and for derivative we require the difference between the error terms, so sensor value previous. This is what we require for the derivative. So let's move on to PID update function and see what it is comprised of. So in this slide we will see how we compute the PID update function. So this is our control law or control input, that is U of t is equal to proportional into error term, that is current error, plus integration into previous sum of errors plus derivative into difference of error. So this is our function, that is PID update, and it has the variable of PID data type, that is pointer. Then we have sensor value and reference value, and these are the terms that we have defined: P term, I term and D term, which we will determine here. And once we know the P term, I term and D term, we will add up these up to get the U of t. And here we have defined the error and difference is basically used for these terms of derivative. So first of all, how we can find the error? We know that from our block diagram that reference value minus sensor value will give us the error. So once we have the error, we can multiply it with the P gain. So here you can see that PID data as we have seen in previous slide, that PID data has variable P gain, D gain and I gain. So we are going to multiply PID data P gain with error. So we will get the P term. Exactly like this, we know that PID data has the error sum. So what we are going to do, we are going to sum the error. So this is exactly like this, error sum is equal to error plus error sum. So current plus cumulative. So this is our current error and this is our cumulative error. So this, we are going to use this term for the integration. So here we have accumulated the error. So I term is equal to, once we have the PID data error sum, we are going to multiply I gain with PID data error sum. So PID data has a variable I gain and we are going to multiply it with PID data error sum. So now we have the error term and now we have the proportional term and we have the integration term. Now let's see how we can find out the derivative term. So for derivative term, we have to find out the difference between PID data has a variable sensor value previous minus sensor value. So we are going to find out the difference between two sensor values so that we can get the error. So we will get this difference. So we are going to find out this every time. So for update for next iteration, we are going to put PID data sensor value previous is equal to sensor value. So this is how first we will find out the difference, because next time this will become P of t minus 1 minus e raised power t minus 2. So we are going to update this PID sensor value is equal to previous. So once we have find out this difference, d term will be equal to this, d term will be equal to PID data d gain into difference, this difference. So finally we have to return p term plus I term plus d term. So if we add these up, so we'll get the u of t, which we will use for actuator. So that is how you can code the microcontroller for PID purposes. So you can make some modification to this code. So until now we have discussed controller design based on a model of a plant. P, I and D values could therefore be determined through quantitative analysis. As I have told you in previous, that on the basis of our plant, if we have a plant, if we have the model of the plant, we can determine the value of P, I and D. So in many cases, however, quantitative determining PID values is not necessary. In particular cases where safety is not a concern and the cost of using the plant is not a major concern either, we can select PID values through a somewhat hit and trial method. So if you do not have a system in which there are safety concerns, so we can just use PID parameter with the help of hit and trial. So start with small value of PID. For example, let's say 0. Increase D until you see oscillation. Then when you see oscillation, reduce D a bit. Increase P until you see oscillation, then reduce D a bit. Increase I until you see oscillation. Iterate until you can change anything without excessive oscillation. So keep on repeating this process as long as you can change the output without any excessive oscillation. So the primary purpose of telling of PID tuning is that, for example, if you have a plant, you can, for model of the plant, you can use that model of the plant to find out the value of PID quantitatively. But for example, if you do not have the model of the plant, you can use hit and trial method to find out the values of P, I and D. So you usually start with the small values. For example, if plant is not available or it is too costly to obtain, what you can do, you can start with the random values of PID, but these values need to be smaller. So you increase D until you see oscillation, then you decrease the value of D, then you increase P until you see oscillation, then you reduce D a bit. So let's move on to next slide. So the practical issues that we encounter while dealing with the computer-based control. Number one is quantization occurs when a signal or machine number must be altered to fit the constraint of the computer memory. For example, if the number is 0.36 were to be stored in 4-bit fraction, then it would have to be quantized one of the following machine numbers. So it means that we have a limited number of bits. So if a number needs to be stored in a computer memory, it must be fit in required number of bits. Second is overflow. It happens if you add two numbers and it gets out of bit. Like if we are adding two numbers like 2 plus 2 and the result is 4, you can represent it with the help of 2 bits. But if you get like 6, you cannot represent 6 with the help of 2 bits. Aliasing is a phenomena when you use sampling frequency less than twice the maximum frequency. So what happens? You do not get proper samples and you skip some samples. As a result, your signal gets distorted, and because of this sampling process you get computational delays. So these are the practical issues that are associated with computer-based control. So in this slide we will talk about quantization and overflow. As I have told you previously that, for example, quantization, you cannot store 0.36 as a 4-bit fraction number. You can store 0.75, 0.59, 0.36, 0.00, minus 0.25, 50, 0.70 and minus 1. So what we have to choose? We have to choose the nearest one, that is 0.25, and this will result in a quantization error of 0.11, because if you add 0.25 with 0.11 you will get 0.36. So sources of quantization are, it can be like multiplication. If you do multiply like 0.50 multiplied by 0.25, so you cannot represent 0.125. I have to take off 5 here. So 0.50 into 0.25 is equal to 0.12. So can use more bit until input and output to the environment / memory. So we have to use more bits if we have to get rid of this error. So one other source of quantization is analog to digital converter. When we are converting analog data to digital data, we have number of levels. Like if we have a voltage level of 4.325, 4.6, so we are going to chop it to, let's say, 4.5 or 4. So there happened to be a quantization error in sampling process. So because first we sample and then we quantize. So analog to digital conversion involves two steps. Number one, sampling, that is chopping off the signal in x-axis, along x-axis, and then quantization means chopping off the signal along y-axis. Overflow cannot store 0.50 plus 0.70 is equal to 1.25, a 4-bit fraction number. We cannot store 1.25 as a 4-bit fraction number because we can maximum go to 1 or minus 1. Solution to this problem is that use fixed point representation. So we can use fixed point representation operation carefully. So we can avoid this. We need to have like 0.5 plus 0.5 so that we do not have overflow like 1.25. So it is time consuming because you need to check each and every number that operation is successful and it is well within the range. The second solution to this is use DSP processor, which are usually floating point coprocessor, and these are very expensive. So these are the two possible solutions. So let's move on to next slide. So as I've told you that quantization and overflow occurs due to discrete nature of computer data, and aliasing is a fact that occurs during the process of sampling. If I have a signal with a maximum frequency of 1 Hz, and if I sample this signal with frequency of 1.5 MHz, so the signal is get an aliasing effect, because our sampling frequency must need to be greater than 2 times the maximum frequency of the signal. So it must need to be greater than 2 Hertz or 2.5 Hertz or 3 Hertz. So if you sample a signal not meeting the Nyquist criteria, you will get an aliasing effect. As a result, your copies will mix up and your frequency will get distorted. Let's have a look at this example. So if you see in this example, we have two different signals. One is of 3 Hertz, the oscillation that are fast is a signal of 3 Hertz, and this one with slow oscillation is a signal of 0.5 Hertz. So if we sample a signal at 2.5 Hertz with a period of 0.4, both of these become undistinguishable, because for this 0.5, 2.5 is okay sampling frequency, but for this 3 Hertz signal we must need to have a sampling frequency of 6 Hertz. So in fact this sampling frequency of 2.5 Hertz can only accurately sample below Nyquist frequency. So 2.5 divided by 2, so we can only sample a signal that is lower than 1.25. So we must need to have a sampling frequency over 2.5 in order to sample this 3 Hertz. So for this, the sampling frequency must need to be 6 Hertz minimum. So time lags are of critical importance in control system. Delay results in control signals being applied later than desired. Obviously, too much delay will result in performance degradation. The effect of delay can be accurately analyzed. For the designer of embedded system, there are two important conclusions. First, analyze at an early stage in the design process the hardware platform and the processor speed relative to the phase lag that can be tolerated. Second, organize the software. So you need to organize the software so that only necessary computation occurs between the time the sensor signals are sampled and the time the control signal is output. And we can move all the possible computation outside of this critical path. So that was about computational delay. Let's move on to next slide. So in this slide we will talk about the benefits of the control system. Control system can be implemented by continuous time or digital time approaches. Since most processes that we are interested in controlling evolve as continuous variable in continuous time, computer-based control approaches add additional complications such as quantization, overflow, aliasing, and computational delay. It is important to consider briefly the benefits obtained through embedded system control. So what are the benefits that we can get from the computer control? Number one is cost, and number two is programmability. Expensive to make analog control immune to. So if you make an analog control, it will be expensive to get it immune from age, temperature, manufacturing error. So all this will affect the analog control. If the time, the temperature, all this will affect the control system of the analog system. Computer control replaces complex analog hardware with complex code. So what we can do in computer control, we replace the complex analog hardware with complex code. So with the help of programmability, computer control can be upgraded. Rather than changing the hardware, we can just update our control. Change in control mode, gain, or easy to do. So we can change the gain, the value of gain, the value of proportional, integrator, derivative. Computer control can be adaptive to change in plant. So as I've told you that our control system is robust. So if there is any change in the plant or if there is any change in the disturbance in the environment, we can get accommodated to it. So computer control can be adaptive. And it is future proof, easily adapt to change in standard. So that was about the benefits of computer control. So thank you very much.